Greetings. This is a video on parametric equations 2, and number 3 will be the last one, and it will concern some applications. This one, however, is concerned with converting parametric into rectangular form and rectangular into parametric form, and we'll do a little bit of applications as well, but this will be on the PDF copy will be on Blackboard, so you can follow along. Here we go. Okay, so part 1 is converting parametric form into rectangular form by eliminating the parameter. I'm going to use some of the examples that we've already seen in the introduction and in the suggested problems in parametric that you work through. So we'll be seeing some of those again. Okay, the first one I want to deal with is the parabolic segment, which is defined by x equals t plus 1, y equals t squared minus 2t for the interval for t from -2 to +4. And basically, as you can see, it's in parametric form. We want to rewrite it in rectangular form. And in plain English, what that means is we want to eliminate the parameter t. So common sense approach whenever we can. I'm looking here and t is clearly x minus 1. So I'm going to take that and substitute it in the expression for y. So here's what it's going to look like. Y equals x minus 1, quantity squared, replacing, minus 2x minus 1 because that was what t is. And you work this out and you get what everybody would recognize as a parabola. If you want to go the extra step and put it into that special form we learned, you can rewrite this, complete the square and move stuff around, and this is what you'd get. X minus 2 quantity squared equals y plus 1, and the coefficient in front of the y plus 1 here would be your 4p, and that would give you, according to the focus, directress, length, last rectum, and all that fun stuff. Okay, along with this, we also talked about the inverse relation, and we just said it's swapping out the x equations and the y equations. So you can see here I did a swap. X is t plus 1, here y is t plus 1, so forth and so on. And you do the same thing. I mean, you solve for t. I'm not going to solve for t here. I'm going to take the easy route, of course. And t is, y minus 1. You do the substitution into the other part, and again you get what looks like a parabola, and it makes sense, right? I'm swapping the x's and the y's, all right? And again, if you want to go through the process of completing the square and putting it in that special form, that would be fine. Okay, all right. Another example which we did was a parabolic segment, and it was retraced. I think what happened is it started in the lower right and retraced its path, and that was kind of interesting. So notice it was not a full parabola, so what we're going to need to do when we get our rectangular form is we're going to have to specify a domain. All right, so at any rate, here we go. You get x is sine t, y is cosine of double t in the interval from 0 to 2 pi. And here's where we have to have pattern recognition and remember our trigonometry. So cosine of the double angle has these three forms, and since the parametric representation has just a sine t, I'm clearly going to use cosine of the double angle 1 minus 2 sine squared, and of course we're using t here and not theta just because that's the parameter. And we're going to substitute in. It's kind of easy. I mean, cosine of 2t is the y, sine of t is the x, so you get 1 minus 2x squared. Again, we recognize that's a parabola, and you can check things out, but x is going from -1 to 1. Okay, so just a note, the bounds on the parameter t determine how much of the curve is actually plotted. So therefore, that's why it's necessary here to come up with a domain, because otherwise if we just wrote y equals 1 minus 2x squared, that would imply that x could be anything that is permitted. That's the general rule if you don't see a specific domain. Okay, so moving along, another one of the examples we had seen was this. X is -2 plus 5t, y equals 1 plus 4t. Turned out that that was a line, and we could of course pick one of these parts, solve for t and sub in, or an alternate approach. We could use a system of equations, which by the way is chapter 12, the next chapter, and we're finishing up here with this topic, parametrics, finishing up chapter 11. So all of the problem sets that we've done on conics, let's see, we've had parabola, ellipse, hyperbola, rotation of axes, and probably one on this. There'll be 5 of them. Those will be totaled up to make this next exam, which, if we numbered it, it would be exam number 4. It'd be all the material from chapter 11. Okay, but system of equations, that will be starting the next chapter, I guess chapter 12. Okay, so the idea is if we want to eliminate the parameter t, we know from experience we want to get the coefficients either exactly the same, we can use subtraction, or opposites, in which case we'll use addition. I always like adding because, well, many students have difficulty with subtraction of signed numbers. So here's what we do. We got 5 and 4 as the coefficients of t, so I'm going to make one of them negative, so I arbitrarily multiply the top guy by -4, I get this, the bottom guy by +5 and get this, and then you can see that these have opposite signs, so I'm just going to add them up, and I get 5y minus 4x equals 13. Okay, so that would be our linear equation, our line. And if you want to put it in y equals mx plus b form, then you could figure out the slope and y-intercept and all sorts of other interesting stuff. But right now we're just going from parametric form into rectangular. Okay, number 4, kind of tough. I mean, you'd have to solve a cubic, and so no simple way to solve this. So we're just going to leave this one, and rest assured, if there's a problem that I ask you to do on a problem set, it pretty much means that there's a relatively straightforward, a simple approach. Okay, I also asked you to look at some exercises I put up on Blackboard, which involve sine and cosine. Turned out to be a circle, and here's why. I mean, if you're looking at this, thinking, well, how can I get rid of the t? Well, you've got to use some trigonometry here. And we're going to use the fact sine squared t plus cosine squared t is 1, so that leads us to the idea of squaring each of these equations. So I'm going to get x squared is r squared sine squared t, and y squared is r squared cosine squared t. Take out the r's, and you got Pythagorean theorem here, so that's a 1, so that's just r squared. So if I added them, I get x squared plus y squared is r squared, which is a circle, center, the origin, radius r. Okay. All right, so now let's go the other way. Let's convert rectangular to parametric. So one of the examples that I'm showing you here, I mean, this is not as bad as it looks. We've got a parabola. And clearly, if we want to get a t involved, the easiest way to do it, not the only way, but the easiest way, is to simply let x equal t. All right, so if I make that substitution, and then y would be t squared minus 4, this is what I would get. Okay, so this is a parametric representation of that parabola. It's kind of shockingly easy, not all that easy, but this one was. And since we don't have a domain here, x can be anything. We know it basically a parabola can have any value of x in this case. So t would go from -infinity to infinity. And just to let you know, that parametric representation is not unique. What I could have also done is I could have said, okay, let's let x be t cubed arbitrarily, and then y would be t cubed squared, which is t to the 6th minus 4, and you would get this parametrization. So it's not unique. So just keep that in mind. And let's look at something now that's a little more of an application. Okay. Get a little more room here. Okay, let's parametrize, that's the verb form, the motion of a particle which moves clockwise, the way the hands of a clock move, about an ellipse, x squared plus y squared over 9 equals 1, so that at time t equals 0, the particle is at 0.03, so in other words, it starts here, and we want it to go around at a certain speed. We want it to make a complete circuit of this ellipse in 1 second. How can we come up with that parametrization? Okay, so here's what we do. We're going to begin with x equals sine of omega t, y equals 3 cosine omega t for some constant omega. This is a Greek letter. And it turns out we typically use omega in this context when we are talking about speed, because I'm talking about, it's going to go around in 1 second. So your next question is, well, how did, where did this come from? Well, first of all, let's see if it satisfies this equation, all right? And then I'll show you how we make this choice. Well, first off, notice that if I solve for cosine t here, I get y over 3. And then and these terms are squared. So if I square x, I get sine squared of omega t. And if I have this in y over 3 and I square y over 3, I get y squared over 9, which would give me cos squared of omega t. And using the Pythagorean identity, that's of course equal to 1, so that's how the 1 appears. So you can see that these choices for x and y certainly do give us this ellipse. Okay, so now why sine here and not here? Okay, so let's take a look at that. And I'm going to shrink this down a bit. And notice I drew a quick cosine and sine curve. The sine curve, of course, is in red. And cosine curve, of course, is in blue. And this is important right here. For the motion to be clockwise, notice that as t increases, x increases and y decreases. Let's see what they mean by that. So if we're starting here, and if we start at time t equals 0, then as t increases, we're going to move in this direction as indicated by the arrow, and also it's clockwise. And notice as we move in this direction, the x value is increasing, and the y value, because we're going lower down, is decreasing. So what we want to do is we want to match these up with sine and cosine. So notice that the sine curve is increasing, x is increasing, so that's why the sine goes here. And cosine in blue is decreasing, and that's why that goes with the y, because that kind of behavior of sine and cosine mirrors what's going on here. So you may have to read this a couple times to think about it, but again, we start here at time t equals 0, and as we move, notice the x is getting greater because we're moving to the right, and the y is decreasing because we're moving down. So that's why this is going to be the sine, because sine is increasing, and that's why the y is going to get the cosine, because cosine is decreasing. Okay? So that's why this choice, sine and cosine, is the appropriate one. Now we know why the 3 is appropriate, because it satisfies this equation. Now the next thing to do is to get omega. Okay, the period is 1 second. Now we've learned when we started graphing trig that period for sine and cosine is 2 pi over the frequency, and omega is playing the role of the frequency. So to say that the period is 1 second is equivalent to this simple equation. So 2 pi over omega is the period equals 1 for 1 second. We solve for omega, and omega is 2 pi. So that gives us this representation. X is sine of 2 pi t, y is 3 cos of 2 pi t for t equals 0 to 1, and that would be the parametrization of this path in this direction, starting at t equals 0 right here. Okay, so that's something to think about. Okay, and just as an emphasis here, omega is often used to model the speed of a particle, and when it's put in here in a form of trigonometry, it's also going to be the frequency, and that's how we use this. 2 pi over frequency is the period. Okay, so if you understand that, then we should be able to apply it to the next one, which is almost the same thing, except this time we want to parametrize it so at time t equals 0, the particle starts here, and it goes counterclockwise. And to throw a little spice in here, we're now going to say we want one revolution to occur in 2 seconds. Okay, so let's, we sort of know that this is the basic pattern. Now, notice I changed up here. Over here, we had x was attached to the sine, y is attached to the cosine. Here, we've got it reversed. So let's see why that is. Okay? Also notice that the 3 has to go with the y because we have this construct here, y squared over 9. So if we solve y over 3, that gives us the sine of omega t. So y over 3 quantity squared gives us this expression. So once again, this is another set of choices which will make our ellipse. Okay, so the question is now again, why is the cosine here and the sine here? And notice that's different than the setup we had originally. Well, that depends, of course, on where we're starting and the direction that we're going in. So let's take a close look at that. At this point, we're starting at 1, 0. We're going counterclockwise, okay? And notice that well, this is a t equals 0, right? So as time goes on, our motion is in this direction. Notice that x is decreasing because we're moving left. And notice that y is increasing because we're moving up in this branch anyway. So that's exactly what's happening here. So notice that x is decreasing, so that's why it's matched up with the cosine, because cosine's decreasing. And notice that the y value is increasing, and that's why that's matched up with the sine. Okay, so that's the reason why the cosine is here and the sine is associated with the y. Okay, so you just have to think about these things a little bit, and it's helpful to have this little plot. And here we go. Okay, we're told the period is 2 seconds. So I should have had an S there. So at any rate, 2 pi over the frequency. So 2 pi over omega equals 2. So 2 omega is 2 pi. Omega is 1 pi. And there we go. So this would be the parametrization of the motion in the elliptical path. This is the elliptical path right here. X squared plus y squared plus 9 equals 1. Starting at t equals 0 at 1, 0 and going counterclockwise. Also notice that the interval is from 0 to 2 because we have a 2-second period. Okay, so not easy, but interesting. Has applications. We'll look at some applications next time. Okay, so adios.